Alrighty, so we're at the 1.7 learning target, periodic trends. This is a big learning target. Really important, have to know it. And it goes along with Coulomb's law, which we talked about in class the other day. But basically, you need to know how and why the properties of elements change as you go left to right on the periodic table versus up and down. So the learning objective is to explain the relationship between trends in atomic properties of the elements, analytic structure, and periodicity. So periodicity, that's a key word you have to know, and that means that every row you go down on the periodic table, the pattern will repeat. So each row on the periodic table is called a period. Periodicity means that every period it repeats. So if, I don't know, the ionization energy goes up across a period, then the period below that, it should also go up, and then the period below that, it should also go up. So the same thing should be happening every period of the periodic table, which is why it's called the periodic table. Okay, here's the other one. The organization of the periodic table is based on the recurring properties of the elements and explained by the pattern of electron configurations and the presence of completely or partially filled shells and subshells of electrons in atoms. Writing the electron configuration that are exceptions will not be assessed on the AP exam. So there's some rules about electrons and about whether they have the lowest energy or not. So ground state atoms should always be in their lowest energy configuration. And there's some weird rules that dictate whether or not what you actually learn with the Aufbau rule covers all those categories. Most of the time it does, but every once in a while it doesn't. I think they're called Hund's rules. You can look those up if you really care, or come see me and I'll teach them to you, but they will not be on the AP exam. So in general, other than the exceptions, elements in the same group on the periodic table all have similar electron configuration endings. So all of the elements in the third box in, I have a periodic table over here, maybe I can do that. Ta-da! Ooh, technology is amazing. So this is referred to as the S block of the periodic table because all of these elements, electron configurations, end in S1. All of these end in S2. If we jump over here, this group of 6 is the P block because all of these end in P1, P2, P3, P4, P5, P6, etc. So that's a pattern based on electron configurations. And let's move you back to the smartboard. Great. Touch, touch, arrow. There we go. Trends in atomic properties within the periodic table can be qualitatively understood through the position of the element in the periodic table, Coulomb's law, the shell model, and the concept of shielding / effective nuclear charge. I'll go through all that soon. Those are the 4 periodic trends that you have to know. Hopefully you know what those definitions are. If not, I'll go through them quick. Should be review from your first year of chemistry. Do I go through them one by one? I do not. Let's check later, actually. I do go through them one by one. Cool. All right, so what we have to use to describe and explain these are these concepts. The first one's Coulomb's law. The farther away an electron is from the nucleus, the weaker the attractive force. And the more positive a nucleus, the stronger the attractive force. So we're talking about the interaction between the nucleus and one electron. Not all of them together, just one. And it's only the ones on the outside, the valence electrons. So if you're farther away, if you're a valence electron and you're farther away from the nucleus, that attractive force will be weaker. If you're an electron and the nucleus is more positive, that'll be a stronger attraction. Effective nuclear charge happens to be the same as the number of valence electrons. So if we think about an atom, there's anywhere between 1 and 8 electrons on the outside ring, right? And then there's a nucleus in the middle. There's going to be electrons in between those 1 to 8 valence electrons that are going to block the nucleus from those outside electrons. Those are called shielding electrons. The core electrons will basically block the attractive forces between the valence electron and the nucleus. So the way that you calculate this is you take all of the protons in the atom. So if we're talking about, for example, calcium. Calcium has 20 protons, so you'd think that would be a charge of 20 interacting with that one valence electron. But calcium only has 2 valence electrons and 18 shielding electrons. So you take the 20 protons, you subtract the 18 shielding electrons, and you end up with an effective nuclear charge of 2, which happens to be the same as the number of valence electrons. That will always be true. The effective nuclear charge of any element is always the same as its valence electrons. You should write that down. Did that. Okay, and then the shell model, electrons on a higher shell are further away. So the shell is related to the period that they're in on the periodic table. So elements that are farther down on the periodic table have more shells, so their electrons are further away. Here we go. As you go down the periodic table, this is what happens. You have more energy levels. 1 energy level here to 7 energy levels there. So according to Coulomb's law, there should be a weaker attraction between the valence electron and the nucleus. There's also more core electrons. So that means there's going to be a greater shielding effect, which again is going to mean a weaker attractive force. So as you go down the periodic table, the attractive force between the valence electron and the nucleus is weaker. As you go that way on the periodic table, you have more protons, but the same number of core electrons. So when you add electrons as you go across the period, this is S1, S2, P1, P2, P3, P4, P5, P6. As you do that, you don't add any more core electrons. The core electrons stay the same, but what happens? You're adding protons. So now my 1 valence electron, it doesn't matter if it's got 1 valence electron or 8 valence electrons, we're talking about the interaction between 1 valence electron and the nucleus. If I'm talking about, what element is that? Neon? If I'm talking about neon over there, it's 1 valence electron doesn't interact with those other 7 valence electrons. Those other 7 valence electrons don't get in the way of that 1 electron that we're talking about. So as I go this way, the only thing changing is my nucleus is getting more positive. So that's going to increase the attraction as you go right on the periodic table. So as you go down the periodic table, the attraction gets weaker. And as you go right on the periodic table, the attraction gets stronger. We can then use that to explain all of these. So ionization energy is the energy required to remove an electron. This is the highest when the attractive force is the strongest. So where is the attractive force the strongest? Well, to the right of the periodic table. So these should have the highest ionization energies, and to the top of the periodic table. So these should have the highest ionization energies. So that means the absolute highest ionization energy is up in the right-hand corner, helium. Atomic/ionic radius, the distance from the center of the nucleus to the outermost of the electron. This is going to be highest when the attractive forces are the weakest. Because if the attractive forces are the weakest, they're going to be able to spread out more because they're not getting pulled in as strongly. So the weakest is then at the opposite corner of the periodic table, which is francium. The third one, electron affinity. This is the energy released when an atom gains an electron. So we're gaining an electron. This is going to be the highest when the attractive force is the strongest. So if I'm gaining an electron, that energy is released more if that attractive force is stronger. So again, we're going to go to the upper right-hand corner, but noble gases can't gain electrons because they already have full octets. So fluorine is going to be the highest. We're not going to worry about noble gases. And then a similar thing for electronegativity. When chemicals covalently bond, now there's 2 nucleuses. Electronegativity is only talking about the 2 shared electrons going around those 2 nucleuses. So in a chemical bond, see if I can draw one here. Hopefully you can see it. We'll do carbon bonded to fluorine. Of course, carbon can have more than one bond, but those nucleuses are different. Carbon and fluorine have different nucleuses. So these 2 electrons are going around both nucleuses. Fluorine has an effective nuclear charge of 7, because it's got 7 valence electrons. Carbon has an effective nuclear charge of 4. So if I'm these 2 electrons, I'm going to be more attracted to fluorine than carbon, because fluorine has a higher effective nuclear charge. So that means I'm going to spend more of my time around fluorine, and we call fluorine the more electronegative element. So the stronger the force, the stronger the forces between the valence electrons and the nucleus, is going to have more electronegativity. So that's fluorine. Again, noble gases don't bond, so they don't have electronegativities. On some electronegativity charts, they will actually give you values for krypton, xenon, and radon, because if you heat them up to like 10,000 degrees, they do end up forming covalent bonds. And that's it. Hopefully, you'll have some practice with that and you'll get better.